This is Learning Assessment Problem 11.7. The problem-solving strategy here is that of three-phase balanced AC power circuits. We are shown a three-phase network in which the source is delta connected and the load is Y connected. We are asked to compute the magnitude of the line voltages at the load. So this would be the VAB magnitude, for instance. The line voltage, VBC, and VCA. In the circuit we have a load impedance Z sub L and the transmission line impedance Z line. The magnitude of the source voltage is 208 volts line to line for each phase, and we would expect that there would be some voltage drop along the transmission line, so the line voltages at the load end would be less than the voltages at the source end. As indicated in the text, we should think Y, that is, convert a mixed system such as this, a delta connection and a Y connection, all to one equivalent Y circuit, and then we can work on a single phase of that Y circuit and solve for currents and voltages as necessary. The equivalent Y-connected source would have a voltage of VAN to neutral of the given VAB voltage divided by the square root of 3 at an angle of minus 30 degrees. That is, the phase voltage lags the line voltage by 30 degrees. This would equal 208 divided by the square root of 3 at an angle of 0 degrees minus 30 degrees, which is equal to 120 at an angle of minus 30 degrees volts for that VAN phase voltage. So the equivalent Y circuit will be drawn next. So this is the equivalent circuit for the A phase. We have the phase voltage source, VAN, the phase current or line current, IAA, the transmission line impedance elements and the load impedance elements, and eventually we want to calculate the magnitude of this phase voltage at the load end, V capital AN. Total impedance that the source sees, Z sub T, is equal to 0.1 ohm plus J 0.1 ohm plus 10 ohms plus J 4 ohms. And this Z sub T has a polar value of 10.90 at an angle of 22.094 degrees ohms. Now we'll calculate the magnitude of the line current I sub AA, and that will equal the magnitude of the phase source voltage V sub AN divided by the magnitude of that total impedance. And that's equal to 120 volts for the magnitude of the voltage source and the 10.90 ohms. And this gives us a value for that line current magnitude, 11.009 amperes. Now we can calculate the magnitude of the phase voltage at the load end. So Z sub L is equal to the magnitude of 10 plus J 4 ohms, and that is equal to 10.77 ohms. Now we can apply the AC Ohm's law. The magnitude of this V sub capital AN phase voltage is equal to the magnitude of the load impedance times the magnitude of that phase current. And that will be equal to 10.77 ohms times 11.009 amperes, or the voltage at the load end of this system, V sub AN, is equal to 118.57 volts RMS. Now we we're asked to determine the line-to-line voltage, so we'll have that VAB, that's the line-to-line voltage between the terminals A and B at the load end, will equal the square root of 3 times this phase voltage at the load end, and that will equal the square root of 3 times 118.57 volts, or VAB will equal in magnitude 205.4 volts. Then, since this is a balanced system, we can say that this magnitude VAB is the same as the magnitude of the VBC line-to-line voltage, and that's equal to the magnitude of the VCA line-to-line voltage.